Hello everyone, my name is Reese Steinler. I'm a junior here at West Virginia University, and this summer, through WVU's SURE program, I've had the pleasure of working under Dr. Cebulski and my mentor, Allison Arnold, studying ionic polymer metal composite electronics, or IPMCs for short. So, a little bit of background. IPMCs fall under this umbrella of soft robotics. And basically, soft robotics are a way I always thought was bendy robotics. They bend instead of traditionally moving in or out. And so right now the current problem with soft robotics, and the reason you don't see them anywhere, is that they really are big and they're bulky and their power sources are huge. IPMCs are the answer to this, and that is what I've been working on this summer. So an IPMC is really thin, we're talking less than a millimeter, and you can really, if you wanted to, power one of them with a AA battery. Way easier than the current solutions. The reason you don't see these everywhere in all these new biocompatible solutions is because the IPMC has to stay wet. And that is where my research has fallen this summer, and where I argue that if we fully encapsulate a hydrated IPMC with hydrophobic coating, then we can sustain its performance through a period of time. So, we needed some concrete objectives before we started working. So our objectives, we needed to determine a coating material. We chose NanoSlick NS200. We needed to establish a coating method, so a way to actually coat them, a wire connection method, and then we needed to figure out how we were actually altering the IPMC's performance. So, first we had to attach the wires. And so our first way to do this was lead tin solder, which is the typical, if you go to Lowe's or anywhere they're going to have lead tin solder. And this was awesome. It was really strong, it was really quick, it was really easy, but it damaged the IPMC. And you can see this is the lead tin solder. And the reason it damages it, because it has to stay out of this glass transition temperature range of 130 Celsius, and 200 is way too high for that. So that led us to silver epoxy. And silver epoxy was okay. That's the best way I could describe it. It was an A and B part mix. It was really difficult to put on. It was an oven cure, and it often broke. It was a really, really weak bonding to the surface. So our last attempt was Indian tin solder, and that's what this process is right here, and this film right here. And this was really good. It was strong, much stronger than silver epoxy, but it was really difficult to use because you had to get the film and everything to this exact temperature of 117 C. So once we had this connection, we then had to go and actually coat these. So the way you would do this is attach the wires, rehydrate them in water, and then after that you'd use an auto dip coating machine to get a consistent coating every time and dip it in this coating that we established, NanoSlick NS200. Then we cured it according to the actual directions. So you can see that there. And a way we quantified how well these IPMCs worked is through electrical parameters. So that's your capacitance. Mainly was our big one. And you can see right here, permittivity is just another fancy way to say capacitance, and you can see that. So the reason that it may look like the unmodified, the red IPMC is better, actually, there is an actual reason for this. So right here at this line, the coating is working for these blue IPMCs. So these red ones, the unmodified ones, the no coating, they're absorbing all this moisture from the humidity chamber that they're stored in. So RH is relative humidity rehydrated. And we know this for sure because we actually went over here and we saw it. So we pulled them out of water and we said, okay, how are these things going to work? And you can see the blue one, which is the coated ones, worked much better than the red ones, the uncoated ones, which means this coating does work. It's hydrophobic. It's stopping the moisture from leaving. So what did we take away from this? It's a good coating, but if you notice back here, it's not perfect. We're not getting exactly what we wanted. So why is this? NanoSlick it's a suspension is what it's called. It's basically NanoSlick, the actual thing, dispersed in some sort of liquid. So that's causing a lot of problems. And in the future, maybe we can look at evaporating it in a different way or combining it with these things called dielectric gels to hopefully fix this problem. And then, so for soldering, by far the best option is to use the low temperature solder. The only problem is it was really fickle to work with, so maybe using some sort of spacer in the future would really help solve these problems and get a really consistent coating. Lastly, I would like to thank Dr. Cebulski and Allison Arnold for this would not be possible without them, and most importantly, WVU's SURE program. Thank you so much.